In this video, I will be discussing about response surface methodology. It is one of the factorial case of designs, like experimental designs I can term. We have seen earlier factorial, Taguchi, response surface designs. So this comes under the category of response surface designs. So let me go through some glimpses of what is this response surface methodology. It is shortly termed as RSM. So this RSM is used where several variables are influencing. For example, I am having only few factors influencing the design. Then I will try to prefer Taguchi or full factorial. If more variables, more factors are going to be influenced, then it is going to be used. This response surface is going to be used to predict the optimal responses. And coming to the definition point of view, it is a statistical and mathematical technique which is used for developing, improving and optimizing the process. So if you compare this one with Taguchi or full factorial design, the total experimental design will be totally different. So I will take a simple analogy. A chemical engineer is there. So this chemical engineer, she needs to estimate the temperature as well as pressure for one particular chemical, and how it is trying to affect the yield, and how it is trying to affect the yield. That is what her experiment is. So yield, basically what we will try to represent is, yield will be represented in terms of input functions, that is the reaction temperature or the pressure. Because we will take the same example in the demo also, that is mathematical calculation demo also we will take the same example. So temperature and pressure are going to be used. See, this temperature and pressure is a function of the yield, and apart from that one we will have some epsilon, then that is going to be represented as response surface. And efficiency means, if I try to talk about the response surface, means this is nothing but the function of both the temperature and response. Next, here how we have to analyze this temperature and response. If you see this particular graph, for example, I need to estimate the efficiency of this particular a particular room. So basically efficiency of a particular room can be estimated depending upon the temperature of that particular room as well as the volume of the room. If volume increases, temperature increases, efficiency also decreases. So I need to establish some kind of air conditioning to that particular room. What happens if volume of the room increases, then efficiency totally it will get reduced. Is it or not? Because temperature is getting increased. So here, if you try to observe, this particular graph is trying to show us an input in such a way that here our efficiency, that is in our example yield, temperature and volume of the room are nothing but temperature and pressure. You can assume like that. You can take multiple number of examples. I am taking like this. Okay, a room is there. So if we are trying to plan to go towards the top surface, that is the maximizing that particular response. If you are coming towards this downside, it is cutting but minimizing the response. If you observe at 45 efficiency, the temperature levels are high. Is it or not? Because efficiency is low means what? Temperature in that particular room is high. Even the volume of room is also less. Like that, the graph we have to analyze. Here, how we have to justify that one? That we have to justify that one in terms of some kind of mathematical equation. That is, we are having first order polynomial, second order polynomial, third order polynomial. Here maximum we will take up to second order polynomial. In some cases that depends upon, even see, when we have to fix that, we should have to fix only up to one particular order polynomial. It is totally depending upon the type of application which we are going. Here some researchers, they will try to stick it to first order polynomial. So basically the equation will be b naught some constant plus b1 constant into x1 plus x2 and so on up to how many number of variables are there. Apart from that one, we are having second order polynomial also. So second order polynomial means where we will have some kind of interactions like x1 square, x1 into x2, like that some kind of interactions will be there. So these are the two cases of mathematical models. We can go up to third, fourth, fifth order polynomials also. Okay. Next, so what is this method of steepest ascent and steepest descent method? See here, if you try to observe this particular graph in the previous example, In the previous example, we can see if we are moving towards the downside, it is called as descent. If you are moving towards upside, it is called ascent. Okay, steepest ascent means maximizing the response, maximizing the output. Descent means minimization, coming towards the dip. This response surface methodology is going to be talk about this steepest ascent and steepest descent only. So here I can able to show that the direction of the steepest ascent in which the y increases rapidly. Here if you try to observe, it is increasing rapidly, and this direction is going to be termed as fitted to the response surface. Okay, and here basically this takes the parts of ascent line, whatever the line which we are trying to represent here, through the center region. To the center region means if you open the previous graph, to the center region, to this particular part, because this is the peakest point, to the center region of interest and normal to that particular fit. So this is the way this steepest ascent and steepest descent is going to be work. Next one, what are the types of responsive surface designs? Because in Taguchi also we are having some kind of mixed levels like that, no? So here what are the types of design? Here basically there are two categories. One is a central composite design, the other one is box beacon design. These are the two categories. So in the central composite design, we will term this one as one of the most popular design. Most of the researchers, they will try to prefer the central composite design. I will explain why this is a central design in the next coming slides. Okay, here what happens means we will have only two levels. Factors will be n number. That is what I started initially. I have said that. So once the response variables are more, okay, once the more number of factors are influencing, so here the levels will be constant, that is 2. So factors will be vary, and here it will have the center points as well as the axial points are also added here. That is the thing with the central composite design. Whereas in the box bend design, it is also one kind of a fitting responses. Here in the previous case we will have center and axial points, but here corner points will not be there. Okay, and here the box bend design can be completed in very less number of runs compared to the central composite design. So that is the basic differences if you can see. And coming to the methodology, how we have to formulate this one is, first thing is we have to develop a lower order polynomial thing by using some kind of design of experiment, and whether we have to test that it is moving in the vicinity of the optimum or not. So whether by conducting the experiment or following the steepest ascent and steepest descent method, we have to check whether the current range is following the vicinity of the optimum level or not. Next thing is we have to develop a full polynomial model. So whether it may be a first order, second order, third order, fourth order, we have to develop the polynomial model conducting in the optimal vicinity. Next one, optimizing the response. That's all. Only 4 steps are there, very few important steps. In every responsive surface methodology we will get some kind of mathematical formula. And here what are the various kinds of terminologies used, because the terminologies are different from our Taguchi experimental designs. Replicates. So replicates is quite similar only. Multiple experimental runs of the same factor levels. 1 replicate based design, 2 replicates based design, we have to go for twice things. So like that example, 3 factors, 2 levels, like 2 power 3 we are trying to terminate like that. So when to add the replicates? So whenever we are going to predict a model, and this model is going to increase the precision of our experiment, as well as whenever we are going to detect very smaller detection, like my objective is very precise, then we have to take. But all of the thing, this kinds of things are experimental is very costly. But the uniqueness is here you can able to detect the smaller defects. That is the uniqueness. Next, alpha. So if you can see, axial points I have discussed. So axial points are nothing but this one. The alpha determines the distance from the each axial point. So axial level points, each points. And this axial level points, some of the researchers they will try to term it as star points also. Some of the researchers they will try to term it as a star points also. Don't get confused. Okay. So these comes under the category of axial points. Next one, cube. So cube means the same case only. Here if you try to observe, if I take a plus sign, this will become my CCD. Here 1 point, 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 CCD. Whereas BBD means I have to take a cube here, in this cube, if a cube is looking like this, here 1 point, central point, top 1 point, corner 1 point, like that 8 points will be there, no? So this is the basic case of how we have to differentiate between these two things. Okay, next, cube, the cube points are coded as -1 and +1. Next one is axial points in the cube. So if you try to talk about this cube, the cube will have some kind of a center, plus alpha, minus alpha, plus 0, minus 0, like coordinates I am taking, plus 0, minus 0, 0. If you go to the top, in y axis it will be plus, and y axis down it will be negative. So like these points we have to represent. Similarly, axial points at the center, which will be having at a center. Okay, here we can able to see when we mix these two things, we will get this one, axial points in the center. So this cube means we will talk about only with the box bend hinge design. So in the box bend hinge design, we will have a cube and we will have an axial as well as a center point, but no corner points. That is the difference between CCD and BBD. Next, most frequently asked question is this one. What is the difference between the Taguchi and responsive surface methodology? See, if you can try to observe, Taguchi designs are fully saturated factorial designs. From the factorial experiments only, Taguchi has been taken an orthogonal array concept and he has developed. But here it is totally different. Factorial design augmented with some center points. So we will have the factors as it is, but as apart from that one, we will have them some center and axial points also here. In Taguchi, we will have multiple combinations, like two factors, 2 levels with 1 factor multiplied by 3 levels with 3 factors. But here no multiple levels will be there. In Taguchi, we can able to go for continuous and discontinuous factors also. But here only continuous variables are also going to be used. There we are trying to talking about the signal to noise ratio. Here we will follow the method called as moving towards the top, steepest ascent and steepest descent methodologies. Okay, so that is the basic difference between these two things. What I will do is, I will take a simple demo, simple example, very regular example, where the reaction time and reaction temperature, a chemical engineer is going to check his yield, and this is the experimental thing which he or she has been conducted, the chemical engineer has been conducted. And you don't forget about this x1 and x2, these are the coded values for this one. Okay, 80 and 90 are the minimum levels for reaction temperature. Reaction time, reaction temperature 170 and 180 are the low level and high level, because in responsive surface methodology we have to check whether we have a low level or whether we have a high level. And central points, depending upon the theory, like alpha is basically sometimes it will be root, like that. So depending upon that one it will be framed. Okay, and here if you try to observe, these are the cube points which has been framed, and these 3 are the axial points, and these 3 are the central points. So central points means it will have more number of replicates. Those things we have to select during our selection, in any software. If I try to open responsive surface methodology, it will ask for how many central points you need, how many axial points you need, like that it will ask. So here I have selected as 5 central points, or that experiment has been selected for 5 points. So I am taking the same example. So I will simultaneously open the Excel sheet and mini tab, so that it will be easy for us to correlate with our example. Okay, so let's open mini tab and Excel sheet parallelly. So take the input like this, what I have shown here. Based upon this input, whatever the input values they have conducted, and then we will open the mini tab software. So here first thing is in the stat case. So stat, we have to go for DOE, design of experiments. Then we have to go for responsive surface methodology. So up to here, whether can you able to connect it or not, you please check it, because it is most important that you have to complete these things, and then you have to proceed further. That's the reason. Next, so here what we will select, here we will go for selecting the responsive surface design. Now the screen is going to show like this. Here the central composite design, so minimum should be 2 factors to maximum of 10 factors. In box bend hinge, the minimum should be 3, 4, 5, 6, 7, 8 is not there, 9 is there, or 10 continuous factors. So here 1, 2, 8 is missing. Here
1 is missing. That is the thing we have to observe. So we are concentrating on a central composite design, as I have mentioned it here. It is a CCD design. So I will try to talk about the CCD only. Number of factors, how many factors we are having here. In this example, if you try to observe, we are having reaction time and reaction temperature, 2 factors we are having. So I will select it as number of continuous factors as 2, and I will go to the designs. And this is the crucial case. So here, based upon the layout, actually this layout we have to frame it, but for our convenience, now I am considering this as my data. So 13 experiments are there. So I am choosing 13. And if there is any cube blocks, so cube blocks means you can go here. This is the cube blocks. So -1 and 1. So no need to mention it, but you select it as 13 runs, block is 1, center points total 5, as well as no Q points and default alpha value will be √2, that is 1.414 plus 1.414 minus 1.414 will be there. And the remaining thing for now you do it as a default, whatever the things are there. Then factors. So what are the factor names I am taking? I will consider it as reaction time and reaction temperature. Reaction time. What is the low value and high value for reaction time? 80 to 90. So 80, 90. Next, B factor. Reaction temperature. And what are the values? 170 to 180. That is, low range is 170, high range is 180. I've taken 2 things, just pressing OK. Factors completed, options, randomize the runs, and the results we will get in a separate table. Now I am generating a experimental array. See here, now if you try to observe, whatever this layout is there, the same thing we have got generated. See, just I will copy these things in the Excel. Here we have got 13 runs, as we have. I will copy it here. Reaction time to reaction temperature, what we are getting here. So now what I will do is, because this experimental run is totally different from this experimental run. Here I am saying that I have segregated based upon the cube, axial and central points, but here it is a randomized runs. Okay. Now for 90 and 170, whatever the value is there, this value I will copy here. Means this is the response column, no? Y is the response column. So response column I am copying. And 85, 175. Here is 85, 175. 85, 175. There are replicates. So first value I am copying here. Next time I won't copy the first value, I will go for the second value. Next 80, 180. 80, 180. Here it is there. So 77. I'll copy it here. Next is 85, 167. 85, 167. This is also 77. I will copy it, paste it here. Next is 77.92, 170. 77.92 and 175 is 75.6. 75.6. Next, 85, 175. 85, 175. Already first value I have considered. I am taking the second one. Next, 85, 175. Next, third one. Next, 85, 175. Next, I will take fourth one. I think next 2 things I can take it parallelly, because next one is also 85 and 175. 90 and 180. So 90 and 180 is 79.5. 79.5. Next 92.60 and 175 it is 78.4. 78.4. 80, 170. 80, 170 it is 76.5. 76.5. Next 85, 182. 85, 182. 78.5. Okay. Now I have got some values like this. This is also an experimental array only. just I have considered the axial values and now I can highlight it. Okay, this 90. First I will take the, based upon this classification, I'll go 80, 170, 90, 170, 80, 170, 80, 170. Where is 80, 170? Here it is. I'll give that one with yellow color. Next 90, 170. So 90, 170. This also I'll give with yellow color. 80, 180, 80, 180. Next 90, 180, 90, 180. Okay. Next central points. So here we are having no cube axial points, axial. So axial I'll give it 77. I'll take one more color here. I'll take orange. 77, 175. I'll take a different color so that the differentiation will be there. Here one color, 92, 175, and 85, 163, 85, 163, and 85, 182. So now you can able to observe this yellow color points and all we have highlighted it as cube. Orange color we have highlighted it as axial, and remaining white we can classify it as central. Now I am copying this thing, going to Excel mini tab, pasting it here, and mention it as Y. Y is nothing but response. Here if you try to observe, this is the basic run and this is the standard run. So standard run means first it will set the initial value as 80. Means whenever I am conducting the experiment, I have to go from linearly, no? So 80, 20. Next second experiment, this value has changed to 90, but this value reaction temperature is 170 only. So like that, this run will be there, and this is normal run order. Okay, nothing changed in here. Next, what we have to perform next? I will see. So go to stat, DOE, Taguchi, response surface. Now we are going for analyzing the response surface design. So after analyzing, here what are the responses we are having? Here we are having only one response. So I have selected this one and I am pressing the select button so that it will be appear here. Next terms. So for example, if we are going for quadratic, or we can decide it here whether we are going with a linear equation or whether we are going linear squares, linear interactions, or full quadratic. Full quadratic means it will talks about x1 square, x2 square, x1 into x2. In my second order polynomial, I have shown no, this equation. This is a similar kind of a full quadratic, x square, x2, x1 square, x1 into x2, like this. This is a full quadratic equation. So I will select include the following terms in the form of a full quadratic only. Okay. Next, options. In the options, if at all there is any weightage criteria, then we can give it. Otherwise, leave it off. No, not necessary. And confidence level, we are setting it as 95%. Next, stepwise also here we don't require anything. Here, stepwise it talks about first factor, second factor, start factor, because already we are doing the interaction like that only. So I am mentioning it as none. And graphs, what are the graphs we required? So residual plots if we required. So residual, standardized residual, just regular residuals are more sufficient. And individual plots here we are having histogram, normal plot, residual versus order. So here we can select all these things, whatever necessary. If we need all the four, just press 4 in 1. And if you want residual versus variables also, you can able to say, so which residual and versus which variable you need to have. So, but we don't think so. This is essential right now. Well, let's okay. Then results. So results are more important. What are the outputs which we need to have? Analysis of variance we required, and coefficients, determination coefficients, regression equations. What are the fits and diagnostics also we require? I press OK. Then storage, what are the values we have to get storage? So here I will take coefficients, because coefficients also very important. Fits are required, residuals are required, standard residuals, deleted leverages, these things and all not essential. I will skip it off. Okay. Then just press OK button. So after selecting all these terminologies, press OK button. Wait for a few minutes, it will generate some equations. Let me go one by one so that you can understand it very clearly. First, we will go to the top section. See, it has been a central composite design, CCD design. Two factors, reaction temperature and reaction time, and the base runs are 13, and how many number of blocks and all we have given. It is a 2-level full factorial, it has been considered. As I am considered here in this example, based upon this example, we are having 4 cube factors. Cube points are 4, center points are 5. So here also we are having 5 center points, you can observe here. Then axial points are 4. So totally 5 plus 4 is 9, 9 plus 4 is 13 experiments we have got. And the alpha value we have set it as √2, that is 1.414. Now the first table which we are getting here is an analysis of variance. See, analysis of variance, ANOVA analysis, the most important criteria which we need to observe it here. I think it is visible to all of you. First thing is model, linear model. Linear model talks about only dependent variables, whatever the independent variables which we are having, those things will be displayed here, reaction time and reaction temperature. Square of the linear terms. Square means, for example, reaction time is x1, reaction temperature is x2. x1 square, x2 square, that is reaction temperature into reaction time, reaction temperature into reaction temperature. That will be square terms. Two-way interaction. Two-way interaction talks about reaction time and reaction temperature. And what is the error? So here, these things are all very common. If you know ANOVA, these degrees of freedom is very easy for us to understand. Adjacent squares. Adjacent squares is nothing but sum of the squares divided by degrees of freedom. Mean squares is sum of the adjacent squares divided by error, whatever the error which we are getting. For example, I will calculate it here. Here we have got 28.42, and here what is the error? 0.28. So this divided by that degrees of freedom will give the adjacent mean square, and adjacent mean square divided by the sum mean squares will get this f value. Now f value we have to look it at statistical table and try to estimate the degrees of freedom, then we will get the p value. If you can observe, the p value is up to here, up to this thing, means individual linear terms as well as square terms, the p value is less than 0.05, means all these factors are most significant. Reaction time, reaction temperature square, reaction time square, all 4 factors are significant factors. Only reaction time and reaction temperature, when they are integrating individually, interreaction is not significant. That is the meaning of this particular p value. So this is most important analysis which we have to get from this particular table. And if you go down, we have got the R square also. R square, that is coefficient of determination. We have got it as 98.28. So 98.28 is a best thing. And the adjusted R square is also 97. Earlier in the ANOVA I have said that it should be around 2% variation. So it was there, no problem. Next step. Here, 2 categories we will get: coded coefficients and uncoded coefficients. So basically, we should not consider the coded coefficients. We have to go for uncoded coefficients. That's why in the storage data, I have selected the coefficients. So coefficients talks about this one. In this worksheet, we are having the coefficient, no, these things. These all values are able to see it here. here. Okay, so actually this is a coded coefficient. We have to consider it, and this one is a uncoded equation. So the same thing, instead of 79.94, we will take it as minus 1431. In just changes, it is coded, it is uncoded. So both the things are going to be represented here. Next, here also, if you observe the p-value, only for the interreaction, the p-value is less than 0.05, but remaining and all, only for this one it is greater than 0. Remaining and all, it is less than 0. So it is a significant. Now if I write an equation for this, so what will be the equation here? So I have to write this one like this. What I will do is I will copy these terms. I will copy it here. Just for writing the equation, I will take x1 value side, x2 value, x1 square, x1 into, I will try to multiply it here. Now here I will try to generate an equation for y. Response model is equal to, so here whatever the equation is there, depending upon this format only I will write. So you observe it here carefully. Coefficient plus this into x1. Here I will enter the x1 because this is usual for prediction, no? So I will enter plus this into x2, that is reaction temperature, plus this into x1 square plus this into x2 square plus this into x1 into x2. Now if I try to enter the values here, like for example, I required 80 and 170, I'll get the predicted value here. Since I have considered the I think I have considered the coded terms, I think so. Yes, I have considered the coded coefficients. So coded coefficients means we can definitely get the change in value. Now if I copy this equation, so just for showing the difference, I am trying to show it. Now if I copy this equation, I can able to differentiate how we are getting the values. See, the same thing I am using. I will write the coefficients here. I will take the coefficients like this. Just I will write this is a coded terminology and this one is uncoded, because in most of the journals they will give this coded and uncoded. That's why I am writing these terms as a separately. Observe 7.81, next 13.27, next term minus 0.5505, that is reaction time into reaction time. Next one is minus 0.04005 and next one is 0.0100. So these are the terms. So I have copied the uncoded also. Now what I simply do is, these two values are common, no? Just I will copy the equation which I have typed just now for the coded. Here I will go y. I will try to copy the equation. Just I will change the terminologies from here to here, shifting, because this will be having a change, but the other thing will not have any change. What is the value we are getting? 75. And 80 and 170, what is the value we are having? Almost close to 76. Okay, so if here 80 and 90 only, so for example we need to have for 92, let's think, and here 180 and 170 to 180 only we are having. I need for 182. I'll get the value as 77 as the response. So every time we have to consider the uncoded equation only in our models. Uncoded only gives the correct case. So I will show the general also. If you see many generals, they will try to give coded equation as uncoded equation also. So here what are the things which we need to highlight is R square value, ANOVA table, that is the interaction table what we have got it from this particular graph. So this interaction table we need to highlight, ANOVA table we need to highlight. Even now we can able to go for this fits and residuals also. So fits and residuals, I'll copy this fits and residuals also. Somewhere here I will copy beside to this one, fits residuals, and I can able to plot these things also onto the graph. If I take this 13 numbers, just insert I will go for a scatter diagram, select the data, add, so add the series name, leave it off. On the x-axis I will take experimental runs, on y-axis I will take the, let me move this one aside because that is distracting. Graph is adjusting, that's why. So I will add it. X range is experimental data and Y series is this data. Okay, and add one more series. You say it as predicted. Same X range is again X values, and Y range is fits. Okay, and this one I will name it as experimental. Now you can see the graph also here, very close to graph. Here in this graph again we can highlight, I think in the data review view, somewhere okay, in the design, I think chart filters, add chart elements. Yeah, this one, add the titles, data labels, whatever the values if we require, legend, and the trend lines. So in the trend lines, which kind of trend line, for experimental or predictor? For experimental, so linear trend line it is showing. Here if you select here exponential, so for experimental or predictor, so it will show all these things. And if you go for pressing the more options, we can see more categories of trend lines. Suppose here we require some kind of a polynomial equation. So for making, it has been changed. Trend lines, more options, experimental, polynomial. Here the maximum order is up to 6. We can do the polynomial equation also, and just press display R square on the chart, equation on the chart, and you will get. And you can see how that R square is there for the 6th order polynomial. It is 0.6, but for us the R square is 98%. If you compare both the things, this is a best thing, is it or not? Sorry, this is a best thing. So we will consider this equation as a best equation. So here the equation we have written it here. So this equation, this is a major equation. And next thing is graphs, which we have seen it in the mini tab. See, the difference between, if I take the bigger graph, the difference between this point to this line, this is a normal line which we are having. If you try to place your sheet here, you can able to see the residuals also. The residuals which are having minus values, it is downside. The residuals which are having plus values, it is positive side, means above the line. Some values are very closer. If you can see this one, it is very closer. It is also almost closer. It is also touching the line. So like that we can able to plot it. And this one, whatever the data, whatever the Y output responses which we have considered here, Y response values, this response data versus the residuals. So here we have got the residuals, no? I am showing the residuals, no? Yeah, here in the graph you will get actually this one. So this residuals versus the values which we have got. And this talks about the observation versus residual order. Observation versus residual order. So whether it is a positive. See, if you can see here, 1, 2, 3, 4, 5, 6 points are above the positive case. Here also you can count it. 1, 2, 3, 4, 5, 6 points are above, and remaining points are below. Like that also we can able to differentiate between these two things. But in most of the publication time, we can try to explain these things. I think this is more sufficient. It will fetch a proper inferences from this particular graph. And this is a histogram. Histogram also talks about versus residuals to the frequency. Most of the cases, how much frequency this particular graph is going to be achieved. So this graph. So just simply we can select this particular graph and we can copy it and we can save it wherever we require. Even in the Excel also we can paste that particular graph, I think so. So I have got a graph like this. So we can present these things wherever we require. So this is the way how we are trying to calculate the CCD, Central Composite Design, by using the Minitab software. Apart from that one, even if you can go for further analysis also, here in the DOE response surveys, here most important thing is we can predict the data also. So I am selecting the predict that thing and then entering the individual values. So randomly I will enter. So 70 and 80 is my input data. 76, and here the values are some 170 to 180, 172. Some random you can take in between the range only I am considering here, or you can take beyond the range also, no problem, not an issue. Because these things and all I did not conduct the experiment, these things. So whatever the things which I did not conduct the experiment, that values I am going to predict it here. Apart from that one, most of the things I have conducted some experiment. Sorry, it is 73 and here it is 180. I will take like that. I have taken some values, individual values, options, confidence level as this thing, and here I will select the results, regression equation, storage. I will take the predicted fits and confidence fits also, prediction limits also. Let's see how they think, and view model. These terms has to be get added, and then press OK. So it will show whatever for the predicted values which we have considered. This is the equation. Already we have discussed about this equation in the earlier only. And now if you try to observe here, the predicted value 79 and 177, which is having a 95% confidence level, and it is going to lie in between these areas, and sum of squares fit is also having 0.7. So like that, that fit data will be represented to us. Okay, for all the predicted values. For all the predicted values, you can check it. So this confidence interval is more important, whether it is, so when we are considering with the 95%, whether this 95% confidence level is achieving or not, that is important. So here in this case, 69% is very low, 71% is also very low. Like that, we have to check it. Next step, stat, DOE, response surface, contour plots, most important. So contour plots, I will show it here. In our starting explanation, I have shown one plot. No, these are the contour plots. These are very important in the aspect of response surface methodology. So in the x-axis, I will select the reaction time, y-axis, I will select the reaction temperature, and response is y. And the contours also, for now, I will select the default things, then I will try to change it. Okay. So it will plot me some data. See, what it indicates me is reaction time to reaction temperature. Whenever we are considering the data, the yield is having higher in this region, and when the reaction time is increasing, the response is getting, I think it is dark blue, it will be around 76 to 77. Like that, we have to analyze from this contour plot. That is the reason why we are drawing the contour plot here. Similarly, go to stat, DOE, response, surface plot. So surface plot also, I am considering the same default categories, and then I will get a plot like this. And this is a 3D plot. So 3D plot we are going to plot because if you assume that we are going to climb a hill. So once we reach to the top surface, means we are reaching to the topmost point. So that indicates that the surface has been reached. Like that, here, this is the topmost point, this top notch. Like that, we have to analyze from this case. See here, when the reaction time is at deeper point, the reaction temperature is at low point, the yield is also very, very low, 74. Where the yield will be high at 80 means somewhere around 88 and 175, it will be high. So if you see our data, where we have got 80, 85 and 175, the same inferences we have got here. So 85 and 175, somewhere at the middle we have got the better case. So like this, we are going to take the surface plot also. If you open any research paper, if you take the CCD design, you can able to see all this analysis. Okay. So first thing is we are going to I will now summarize what are the things we have learned so far. So first thing is we are trying to consider what is our basic design, whether it is a CCD design or Boxman Hill. Here I am considering it as a CCD. So I have to fix it, how many number of points, whether it may be axial points or whether it may be a cube points or it may be center points, I have to fix it. So depending upon the points fixing, then I have to go for conducting the experiments. After conducting the experiments, I'll get the yield, that is y value, then take this thing in the mini tab, and then I am going to estimate the analysis of variance, and I will check whether my model is significant or not by checking the R square. Then after considering, I will take the equation. From this equation, I am going to get the predicted values also. After getting this equation, then I will try to go for plotting various curves like surface plot curve as well as contour plot curve. By seeing this curve, I can analyze it very clearly. So what are the things I can able to inference from these things?